வணக்கம். Welcome to this course on biomedical instrumentation.
So far we have been looking at flow meters. We looked at the first set of videos at flow meters, various types of flow meters. We looked at electromagnetic flow meters. We looked at ultrasonic flow meters. We looked at within ultrasonic. We looked at the continuous wave Doppler, pulsed Doppler, then laser Doppler. Then we looked at transit within ultrasound. Ultrasonics. We also looked at transit time, and we looked at thermal flow meters, and then we started looking at respiratory measurements. We spent some time on respiratory physiology. Actually, we have not done justice to the complexity of the respiratory physiology and the physiology of the respiratory system, because I think that respiratory physiology video was about 10 to 15 minutes maximum. That is not really enough time to learn enough respiratory physiology so you can understand the measurements associated with respiratory physiology. However, this is a course on instrumentation. So we focus on measurement and instrumentation. So I request you to invest the time and learn about the physiology by yourself. I have mentioned this in that video also. So I would like to emphasize that point one more time. So then we looked at spirometry. So in this video, we will look at another way in which we can measure breathing. That is called as a pneumotachometers. What is this instrument and how is it used? We will see in future slides. And in particular, we'll also then look at a particular type of pneumotachometer called as a Fleisch pneumotachometer. Then another method for measuring lung function called Plethysmography. We'll look at these things in this video. So what is a pneumotachometer? Essentially, this is a spirometer, a measurement device that is used to measure breath as a flow. Previously, when we looked at flow measurement systems, we were talking about blood flow. But in this case, we are looking at air flow through the mouth as a form of flow. Air is also fluid. So essentially, to measure flow, and we use that to make diagnosis, come to certain conclusions about the nature of the respiratory system, about the breathing system. Earlier, what were we doing? What is the difference between this and the spirometer? Well, the spirometers, we discussed the critical volumes. Recall, what are the volumes that we discussed? We looked at tidal volume, inspiratory reserve volume, expiratory reserve volume, residual volume, and capacities. We looked at those things. But here we look at flow. Recall from our discussion of blood flow. What is the difference between flow and volume? Flow is, if you recall, the time rate of change. That is how much volume of air passes through in unit time. That could be a minute, a second, whatever. That's what we discussed in the blood flow part. When you say flow, you are essentially focusing on the time rate of change. So what is from that? What I can do? I mean, think about this. I am essentially having the time rate of change of volume as a function of time. Then if I would like to know the volume of air in a given unit of time, all I have to do is integrate. I have to find the area under the curve, and then I can find the volume. This is the principle of measurement of pneumotachometer. These are essentially flow sensing spirometers that measure the rate, not the flow. That is not the volume. The difference with the spirometer measures volume, whereas pneumotachometers measure flow, which is the rate during breathing. Essentially, what is the principle? The principle is that there is a drop in pressure across a resistance, and this drop in pressure is proportional to flow. That is, the change in pressure is essentially the product of the resistance offered times the flow itself. And I just have to integrate this flow over time to compute the volume. Essentially, there must be some minimum resistance that the measuring system should offer to breathing, because if there is no resistance that is offered, then you cannot measure, right? Because what are you measuring? You are essentially using that resistance and the change in that resistance as a means to compute flow. So a minimum resistance should be offered, and change in that resistance as you are breathing harder or lower will essentially indicate to you what the flow rate is, which you can then integrate to find volume. That is the idea, right? Think about it similar to water flowing through a pipe. If water is flowing through a pipe, essentially in your home, you are having a water flow meter. If water is flowing through a pipe, and that, let's say this is a flexible pipe, and it is being constricted. If there was no pressure difference between the two ends of the pipe, then there will be no flow. Suppose I'm constricting that, let's say it's a flexible pipe, and I'm with my shoe, I'm just trying to step on it. Then what will happen? Essentially, the resistance will increase. What will this do to the flow itself? That is the question. So essentially, the pressure difference, right? The pressure difference will be created that causes changes in the flow rate, and this will, a similar situation happens in the airflow case, that creates measurable changes in pressure. So, but then if the resistance that you're using to make the measurement is too much, then essentially flow will be stopped. The method that you're using to make the measurement should not affect the measured quantity itself, the fundamental rule of measurement. So the trick, a critical trick, is to make sure that there is minimum resistance so that you can make the measurement, but not too much resistance that it stops the flow, or it otherwise provides an obstruction to the flow. So that's the critical point, and that's what many of us do not, find it difficult to understand or imbibe. So that, right? It's like, if you're, it's like, imagine you are trying to, let me try to think about, let's consider this. Let's say you're trying to drink, say, water through a straw, through a small sized straw, those that you use to drink soft drinks. You're drinking water through the straw, and then you're using the same straw to drink a thick milkshake that has not, to which you have not added water. You have some fruit pulp and you have added milk to it. Say, let's assume that is also full cream milk. And then I use the same size straw to drink. So for a given pressure difference, the flow will be less in the second case now. But why? Why is this the case? Because the resistance offered by the thick milkshake will be different from, say, for example, water. It's like drinking thick milkshake through the regular straw. I'm supposed to imagine that now you are now trying to make a big, drink the same milkshake using a much wider, much broader, or a straw with a larger diameter. Now, in that case, what will be the flow? In that case, the flow will be different. Now, of course, this is essentially an example, but the rigorous method essentially involves a mathematical rigorous, mathematical relationship that is indicated, that is founded on fluid dynamics. Too deep for this course. This is a course on, biomedical instrumentation. So when the flow is laminar, the pressure drop essentially is linear to the flow rate. So that is the point. And you would think, the students would think that higher resistance means better measurement accuracy, but this is not usually the case. There is an optimal resistance window. That is what I'm trying to, giving many examples to make you understand that if the resistance is too small, then you will not even offer the minimal resistance. If the resistance is too high, then that will by itself become an obstruction. So there is such a thing called as a window of optimum resistance in which you are able to make the measurement, but that's not too much that it is obstructing the flow of air itself. No? So you need to identify what that is. Right? And also critically remember that pneumotachometer does not measure volume directly, but rather measures the flow, which you then have to manually or using a computer, using an electronic device, you will have to integrate, because you are interested in finding the area under the curve. You need to perform mathematical integration. That means as soon as you say integration, remember from your high school mathematics that there is such a thing called as plus C in your integrations. That means it is critical for you to identify what the constant is in the constant of integration is. So there will be such a thing called as a zero drift or some value that you will need to find out, and this is true for integration. So you will have to integrate it carefully, because what will happen is that there will be such a thing called as drift, or you will not be able to find a constant. Okay, spend sufficient amount of time on that. The most important, the most critical this is that it is a non-obstructive tool for the patients. And this is the critical thing. Unlike spirometers, which can only be used for a given period of time, pneumotachometers are used for long-term monitoring. Every time I say long-term, I keep mentioning what long-term means. Long-term means what? Years, decades, years, months. From the viewpoint of biomedical engineering, any measurement that lasts more than a few hours is essentially long-term, several days. So ICU type of monitoring or bedridden patients monitoring is essentially long-term monitoring of patients with respiratory difficulty. So that what is the principle? I already mentioned this. So if there is a pressure difference across a resistance like a mesh or a screen, but if the mesh is too thick, then then air cannot flow through it. But if it is too thin, then you cannot measure anything. So the pressure drop is proportional to the rate of flow of air through that, and I can measure the pressure drop. What is the flow rate? Remember what Q is. Q is not volume. Q is liters per second. It has the unit liters per second, which means that you will have to integrate over time to find the volume, whose unit will be in liters. Okay, remember this. And so in this type of pneumotachometers, in particular, there is a type of pneumotachometers called Venturi type pneumotachometers. Find out what is this Venturi pneumotachometers. What is it? There is such a thing called as a Venturi effect and a Venturi throat or a Venturi type design. What is this Venturi? It is beyond the scope of this course to teach you the Venturi effect, but find out how Venturi effect can be used, for example, to cool spaces. Find out how that is done. It will be a useful exercise for you. It's actually not related to biomedical engineering. Venturi effect is an effect in fluid mechanics and fluid dynamics, but it's a very interesting scientific phenomenon that you will find interesting. So I'm leaving that as an exercise for you to learn what that Venturi throat means, what Venturi effect is. Find out what it is. But what is already known is that for laminar flow in a cylindrical tube, the resistance R is directly proportional to the viscosity, dynamic viscosity of the air, and the length of the airway or flow head. So that is essentially, this is known, and this is not really rocket science. We all know this. So essentially, it is the viscosity eta times L. In this case, we are calling it as mu times L. So as like similar to to the length of the cable having more resistance, a longer electrical cable has more resistance. Likewise, a longer length of the tube will have a higher resistance to flow. Now that makes sense. But in the denominator, I'm having pi r power 4, where r is the radius of the airway or the resistive channel. That is, the resistance is inversely proportional to the 4th power of the radius. What does it even mean? Can we even try to imagine this? No, it's a little deep. I want you to invest some time and understand what this means. Imagine your breathing resistance increasing 16-fold. 16-fold, just when your diameter of your airway reduces by half. That's what it means. Instead of R, let's say R1 is some R by 2. Because of, say, you are having an obstructive pulmonary disease, or you are having COVID. Because of some reason, the obstruction has reduced the rate, or you are having cold, common cold. This obstruction, this fluid has reduced the radius of your airflow tube by half. For example, you assume, then your resistance increases by R by 2 to the power 4, no, right? And R is in the denominator. That means R by 2 means that 2 power 4 will essentially go, because denominator, in the denominator there is another denominator. That means that 16 will go to the numerator, which means that your net resistance will increase 16 times. And that is quite difficult to capture. It's an extraordinarily nonlinear effect. It's not. So that means it is extremely sensitive to radius. Not slightly sensitive, extreme sensitive to radius. It's actually a blessing, right? And it is also a curse. It's a both, right? So a small change. If I'm trying to make tubes, measuring tubes, that is just varies in radius just by a little bit, will hugely change my resistance to this. So the tolerances are extraordinarily hard to find. Also, whether the flow will be laminar in the tube or not is determined by the Reynolds number of the flow, which is, and that's a topic in fluid mechanics beyond the scope of my of this course. Essentially, I can determine whether there is turbulence or lamina, whether the flow is turbulent or laminar, depending on this number. And this rates can, the flow rate can be quite huge under this. And you would think that, if there is turbulent flow, it will essentially means that it will add noise, but that is not always true. Turbulence essentially changes the pressure and flow relationship in a way where, your relationship is no longer linear but rather quadratic. It just means that your equations change. That is the nonlinearity that it brings. And you might think that if you have small tubes, the flow inside the tubes will always be laminar, but that is not really true. There can be turbulent flow even in a relatively small tube. So, actually, if the tube is too small, then there will be other things that come into the picture, such as so-called wall phenomena, okay, or the so-called wall effects. The wall of the tube will start having an effect on the flow itself. So there are, and the roughness of the tube and other such things will start to play a huge role as the size of the tube reduces. It's a big topic beyond the scope of this course, but all I'm saying is that the resistance is inversely proportional to R power 4, which means that you need to be very cautious about choosing the right type of tube for this device. Next is the topic of Fleisch pneumotachometer. This is a device that is used to measure airflow rate while breathing, essentially similar to spirometry, right? And in performing the so-called pulmonary function tests, right? And in particular for monitoring ventilators. How well the ventilator is working is something that you need to do, right? The output of the flow transducer essentially appears as a difference in pressure. How am I saying this? Because delta P is R times Q, where R is the flow resistance, which you must know for your tube. How do you know this? During calibration, you will find out what that R is. This is something that you find. Q is what you are trying to measure. Q is what you are trying to measure. And I can find Q using, say, for example, some standard pressure sensor, capacitance transducer, or some such standard pressure measurement system, pressure transducer, because they are more stable in a vibration sensitive system. For example, when compared with resistive system or inductive systems, capacitive systems are more suitable in vibration sensitive spaces where the person might be vibrating or so. But then if the flow rate increases, then there will be turbulence that will develop, and this will make the relationship less linear, and essentially limits the possible range within which you can use. So that means your system can be linear only in a range of flow rates, only in a range of rates. So you need to know what are those specific critical specifications. As a biomedical engineer, you need to know what are the critical specifications of a pneumotachometer within which you will have a linear relationship and a predictable output. Non-linear doesn't mean that it is not predictable. It is unpredictable. It just means that it becomes a lot more complicated for you to predict it. That's what it means. It doesn't mean that it is unpredictable. Essentially, in this case, what you have is that you will have several parallel capillary tubes. There will be, instead of having one tube, there will be a lot of small capillary tubes. Each of them will maintain the Reynolds number to be less than 500, even when the total flow itself will cause turbulence. Remember, the total flow will cause turbulence when all of them are flowing through a tube of radius that is much higher. In that case, there will be turbulence. But if I am sending this flow through several small tubes, then I will not have turbulence. That's the idea. It's like, let us say that I am having a highway through which, I'm trying to make up this example. Let us say I'm having a highway in which you are having extraordinarily disciplined lane discipline. I'm having a 8-lane highway. Okay. I'm having a 8-lane highway in which you are saying that, this car can go only in this lane, for example. Okay, into many parallel lanes, and you are saying these type of cars, the small cars can go only in lane 1, big cars can go only in lane 2, or whatever. I'm giving an example. You are trying to divide the total, the traffic into some type. It need not be cars or vans, or it need not be related to size. I can say that green colored cars will go in lane 1, red colored vehicles will go in lane 3, for example. That essentially, if you assume that the color of the cars are uniformly distributed, which it is not, if you assume that, then I will have relatively smooth flow in each of the lanes. However, if there is no, like in India, like we have in our country, there is no such thing as lane discipline. Well, in that case, there will be chaos, noise, and as we frequently see, turbulence. There will be a lot of turbulence. That is what we call as traffic congestion and confusion. This is something that happens only because you don't follow such thing called as lane discipline. But if you do follow it, then there is no. So laminar flow is that whereby by having several small tubes, you are essentially limiting the Reynolds number to a relatively small value and ensuring laminar flow. That does not mean, as I previously said, that if you have small tubes, you will necessarily always have laminar flow. That is not true always. If the radius becomes too small, then wall effects and other such things will come into the picture. It doesn't mean that there will be no turbulence, but this is a way in which you could approach this problem. Okay. So you need to, in these cases, you can use modern manufacturing methods, 3D printing, photolithography, and you can create really small tubes. Now, what is the size of the tube? In the order of micrometers. Remember, micrometer means then what will be the capital R in that case? You need to compute. No? In the order of micrometers. Yet modern manufacturing methods, for example, photolithography, allows radii in the order of micrometers, and tolerances that are extraordinarily good. That. So we have already seen this, and then we'll move on to the next topic, which is plethysmography. In this method, our interest is to measure lung volumes by finding out pressure differences. How is pressure and volume related? When the patient breathes inside a sealed chamber, if a person is breathing inside a sealed chamber and I am measuring the pressure change that is happening due to the person breathing or a patient breathing, I can essentially find out what the volume is. Now, but how? Because that what is the principle, fundamental principle? Well, imagine you are sitting in a phone booth, which is essentially the plethysmography, the space chamber in which you are measuring. You are sitting in a tightly sealed phone booth, and I am you are trying to breathe. When you inhale, your chest will expand. That means that the volume is increasing. But where is this air coming from? From the rest of the phone booth? No, because it's tightly sealed. No, it's extraordinarily difficult to seal a phone booth. I understand. Let's assume that you are able to seal a phone booth. Then that expansion of your chest essentially compresses the air in the rest of the phone booth. That means that the pressure in the rest of the phone booth will change. Recall from your high school physics or chemistry, I don't recall which subject that is, it doesn't matter. From your high school science, I think chemistry. From your high school science, you have heard of a law called Boyle's law. What is this law? This is P1V1 equal to P2V2. If the total volume of the booth is something, right? And your inhaled volume, let's say the total volume of the booth is, I don't know, say some 700 liters. Okay. And the amount of air that you are inhaling, how much air you will normally inhale? We saw from our respiratory physiology class. Normal inhalation is about half a liter. Is it not? About half a liter. Let's say I'm inhaling about half a liter. Whereas your 700, the sealed chamber, your phone booth is 700 liters. Then the pressure change is essentially by how much? P1V1 is P2V2. Let's say I know the initial pressure, then I could compute the final pressure using, and I could find out. Let's say I can measure the initial pressure and the final pressure, and because I know one of the volumes is constant. Which volume is this? This is the phone booth volume. Is constant, then the rest of the volume I could compute V2 essentially as P1V1 divided by P2, assuming that I am able to make a relatively accurate measurement of P1 and P2. And because P1 does not change, P2 change is happening essentially due to V2. That is all. So pressure variations are measured too, and this is used to find other things like volumes, capacities, tidal volume, residual volume, total lung capacity, vital capacity, all those things. You recall all those things. FRC, inspiratory reserve volume, expiratory reserve volume, residual volume, all those things you could compute. These are essentially derivatives of the original volume. So this will be extremely accurate, right? Because even for volumes that simple spirometry cannot assess, this will be accurate. No, but what is the critical challenge in this? The critical challenge is that you need to have that sealed container, right? An assumption that you're making is that in this case, so has a constant pressure and a variable volume. Not when the thoracic volume changes, the gas is going to get displaced. But what we don't recall is that the person breathes through a tube from outside. Okay, not from inside. The person breathes through the tube from outside. We only measure the change in the chamber volume or the chest volume change by measuring the pressure change. This is what you're changing this. And you might think that one might think that the bigger rooms or bigger chambers will essentially give better measurement. This is not true. Actually, as the volume of the room keeps increasing, the possibility of you making it more and more seal proof is difficult. That is one. Also, the amount of pressure change that you are going to get in a large room is going to be much more minute, essentially affecting the sensitivity of your measurement. So for you to have sensitivity, you need to have minimum volume. But of course, if you have the volume too low, then the person will feel claustrophobic or it's a very scary experience. So that is it's critical to find out what is the sweet spot where the person is not feeling very scared, but at the same time we are able to get accurate measurements. So there are several challenges. Remember that, and the other thing is that not only lung volume, but gas compression, volume change in blood, even if you are talking or something as you are inside, all these things affect measurements. So it's a relatively, relatively serious, complicated procedure, but it measures the flow rate with a relatively good accuracy. So with this, we come to the end of this video. In this video, we looked at pneumotachometers, a particular type of pneumotachometers called the Fleisch pneumotachometers, and we looked at plethysmography and the advantages and disadvantages associated with plethysmography.
With this, we end this video. Thank you for your interest and attention.